me, and I may have to give me one. Okay, the second law of thermodynamics is the law of entropy. I'll say that again. Entropy just means randomness. Okay? It says that everything basically wants to be random. Okay? That is the second law of thermodynamics. So let me repeat that again. The first law was that energy is neither created nor destroyed. Okay? So it's not created or destroyed. That's the first law. The second law says that things want to be random or in disorder. Okay? Randomness. Does everybody follow me so far? Now you may be saying, well, why am I telling you about that? Well, because when we get ready to look at these cycles, right, and these different steps, I want you to keep in mind that even though we're breaking something down, does not mean it's going to be eliminated. Does that make sense? Everybody got that so far? Okay. All right. So watch this. Let's go with it. Now, what are the things that we can metabolize? What can we actually metabolize? We can metabolize carbohydrates. Yeah, y'all see this? Lipids, proteins, nucleotides. Everybody good with that? Yes, exactly. Perfect. So all those things can be metabolized. Now, what do all those things have in common? What can they all be metabolized to? Like, what's one common thing that is a product of carbohydrates, lipids, proteins, nucleotides? Okay, Karina says atoms. Pedro says ATP. True. I like that, Pedro. ATP is good. But even before you, not NADH, before you get to ATP, there's something else that all of these can be metabolized to. No, not CO2. I love it. I love it. All that action. Good, good, good try. Are y'all ready for this one? All three, good, Pocky. All of these can be metabolized. Something called acetyl CoA. Have you ever heard of that before? Yes, exactly. Don't forget that. Please don't forget that. All of these can be metabolized to acetyl CoA. Okay? Now, watch this. If I increase acetyl CoA, what does that lead to the formation of? What will form from too much acetyl CoA? Good, Stan. Perfect. Good, Pocket. That's right. You can form something called ketone bodies. Okay, everybody see that? So too much acetyl CoA can form ketone bodies. Now, somebody may be saying, what is a ketone body, right? What is that? A ketone body is another source of energy, but it is a real weak source of energy, right? So let me give an example, put it in everyday terms. Say, for instance, I told you, hey, if you eat this, let's say apple or fruit, right? It's a good source of energy. But then if I tell you, hey, why don't you take this candy bar? It'll also give you energy, right? But it may not be the best source of energy. Does that make sense? Okay. So the best source of energy, of course, is ATP, right? Would everybody agree with that? ATP is like the fruit. That's your best source of energy. But a ketone body is also a source of energy, but it's not your best source of energy. Does that make sense? Okay, great. Perfect. All right. I'm seeing the same people responding. All right, good. Perfect. All right, now watch this. That means then, what that means is that acetyl CoA, we need to do something. Can you break down ketone bodies to ATP? Yes. Yeah. Well, you can't. Let me repeat that. You can't break the ketone bodies down. But what you can do, Pocky, is you can channel the acetyl CoA into the TCA cycle to make ATP. So it's a way to channel that. The ketone bodies is basically what happens when the acetyl-CoA is moving too fast, when we don't have time. Okay, so watch this. Y'all ready for this? All right, let's watch this. I'm going to share my whiteboard and watch how we do this, okay? So, say for instance, we have glucose, okay? This is the big overview picture of what I'm going to show you. That glucose, we said, can be broken down, right? And it can be broken down into 2 pyruvates, okay? Stay with me. Those 2 pyruvates, okay, can be broken down, and they can be broken down into acetyl-CoA. Yes, good, Maria, that's right. Okay, is everybody with me so far? All right, now watch this. Stay with me. That acetyl-CoA, okay, what it can do is that it can combine, right, with something called oxaloacetate. So these 2 can combine, and what they're going to do is going to make something called citrate. Everybody with me so far? Now, this cycle that you see right here, we call the TCA cycle. This cycle is also called the Krebs cycle. This cycle is also called the citric acid cycle. Okay? Everybody follow me so far? So the same name, it's the same name used for the same cycle. They call it either citric acid, TCA, or Krebs cycle. Is everybody with me? Okay, great. Perfect. Perfect, perfect. Okay, now watch this. So what Pocky was asking was, can you break down the ketone bodies to make ATP? No, because if you could do that, then that would be a pretty good source of energy, right? So the ketone bodies have their own energy. So what is this? This means then, if my acetyl-CoA is going up too much, right, too fast, all right, it's like overloading my system. When that acetyl-CoA is overloading my system, that means then now I don't give it time to go through the TCA cycle to combine with oxaloacetate. Does that make sense? Okay, good. Now, as a result, guess what happens? That's when I'm going to form these ketone bodies, only because I don't have time, right, to get through the TCA cycle. Okay, now watch this. On the exam, one of the things that they want to know is this. What is the condition? What would make your acetyl-CoA go up really, really high? Like, what would cause it to increase like that? Anybody? Anyone know that? Give me an example of something that you think that would make your acetyl-CoA really increase like that. Oh, Karina. Well, you close, Karina. You're close. Oh, okay. All right. Let's process it. Process it. Ooh, Magia. Magia. I like that. I love that. Watch this. Magia said it, but in a different way. Right? So it's actually starvation. Not sugar, right? Because think about it for a second. If you're sugar, or if you're starving, right? That means, do you think glycolysis will increase or decrease? Okay, Amira says increase. Sakshi says increase. Good, Ruby. Good, Prachi. That's right. Does everybody understand that? Does that make sense to everybody? If you're starving, you're going to increase glycolysis, right? Okay. Oh, good, Jessica. No problem. So watch this. So if we go to the next page over here, This is where I want to go. Yep, that's right. So glycolysis, whole purpose of glycolysis is one, to produce energy, right? In the form of ATP. Okay. So produce energy in the form of ATP. All right, you with me, Jessica? That's the purpose of glycolysis. Now, why do we have glycolysis? What does glycolysis do? It breaks down glucose. Okay, are you with me there? You with me, Jessica? Okay, perfect. So, Jessica, watch this. If the purpose of glycolysis is to make ATP and to break down glucose, if I'm starving, is my energy levels high or low? All right. Y'all are right. Okay, let me tell everybody this. If, like, for instance, if somebody asks a question, that means that they probably don't understand that. So if you answer it for them, that's not helping them. Does that make sense? Everybody got that? All right. So make sure give them a chance to at least answer the question first. You got to give them a shot, and then they will do it. Okay. Okay. So that's glycolysis, right? Breaking down glucose. Now watch this. So if you're starving, when you're starving, the reason that glycolysis will increase is because you need more energy. Does that make sense, Jessica? Okay, great. And if you increase glycolysis, let's go back to this screen. Guess what happens? So if this is glycolysis, the breakdown of glucose, if you increase glycolysis, then you're going to increase acetyl-CoA. Does that make sense now? And that's why you get ketone formation with starvation. Does everybody have that? Everybody understand? Okay. Now I think Stan, you asking what is glycogenolysis? That's just the breakdown of glycogen. Yeah, that's the breakdown of glycogen. So we'll get to that in a second. Okay, everybody understand that? Okay. All right. Any questions on what I just explained? Well, yeah, we're going to get to that. We're going to talk about glycogenolysis, but we need to go through the metabolic steps first. So let me go through the metabolism, and then as we go through it, then we can answer any questions. Okay, everybody follow me? All right, so let's rock and roll. All right, here we go. I'm going to pull up my screen. All right, it should be coming up. Perfect. All right, so here's the first thing. So when we talk about metabolizing things, you remember I told you on probably the first day of class that there are two places in the body. What are those two places? What are the only two places that we talk about? Yep, inside and outside of the blood. I love it. I love it. That means you all are listening to me. That's great. Okay, now that's going to be important because watch this. Watch this very closely. If we're talking about in the cell, inside of a cell, is that in the blood or not in the blood? If we're talking about the cell, that's not perfect. Okay, good. I love it. I love it. Now watch this. So I'm going to draw this little thing right here. The little B represents the blood. The C represents the cell. Okay, everybody with me? Now, watch this. In order for things to get into the cell, there has to be a way that they can enter the cell. Now, this that I'm going to tell you now, it may be stuff that you already know, but I got to tell you, because if you don't understand this, this is going to be trouble as we move forward. So let me go ahead and pull that up, okay? So we're going to talk about how things get in the cell. Has anybody heard of these things like diffusion, active transport? Are y'all familiar with that? Yes. Okay. Is everybody familiar with it? Because that'll really make it go faster. But if you're not, let me know. All right. Everybody should be able to see my screen now, right? All right. Here are the two things we want to talk about. Here's the first one. Okay. So watch this. So if you look at this heel right here, this is a heel, okay? The line that you see from the top of the heel to the bottom of the heel, if you read the notes, what did I tell you this line represents from the top to the bottom? What is it? Yes, Andrea. Good, Amira. Good. Perfect. Good, Stan. That's right. This is your activation energy. I love it. You know what you're telling me? That means I know you studied. That means you looked at the notes. I'm glad. So activation energy, right, is the energy that you need to overcome for the reaction to move. Does that make sense to everybody? Okay, good. Now watch this. If I am going up the hill, do I need energy going up? Yes, good, perfect. So if you imagine the concentration, if we were to graph this hill, right? If you were to imagine the concentration is 0 here and 100 here, right? This is the concentration. That means as we go up the hill, or we're going from a low concentration, right, to a high concentration. Does that make sense? Good. So what we do is we say that we're going against the concentration gradient. Does that make sense? Now, what type of transport goes against the gradient? Yes, Amira. Perfect. Good, Pocky. That's right. That's right. That is what we call active transport because you're going against the gradient. Okay? Now, look at this one. Now we're going from a high concentration, right, down to a low concentration. Now, when we go from a high concentration to a low, what do we call that? Yes, Sakshi, that's right. Not necessary. Now you got to be careful, Mira, because it may not be passive. It depends, right? Because we have two types of diffusion. It can be passive or it can be facilitated. So you got to be. It's just all you know so far is that it's diffusion, right? Diffusion has the letter D in it for dog, right? So D represents down, like you're going down the concentration gradient from high to low. Is everybody good so far? Yes, Andrea, that's perfect. Active is from low to high. Diffusion is from high to low. Okay? Everybody good so far? Now watch this. Now keep this in mind. In order for us, what would make this so much easier, right? If there was some kind of way we could cause this heel to be a little lower. Do y'all see that? The purple line? If we could make that heel a little lower, it would be, the reaction would move faster. Does that make sense? Good. Now, what do we know that can help us? Okay, Ruby said no. Okay, so Ruby, what I'm saying is, if you see the purple line, Ruby? Okay, the blue line is the original line. The purple line is a line that also represents activation energy. Does the purple line, Ruby, mean a higher activation energy or lower activation energy? The purple. Good. It's lower. So the question is, what can lower the activation energy? Tell me something that can actually lower the activation energy. Ruby. Ruby. Oh my, Ruby. Okay. Yes. What can lower the activation energy? Okay. Anybody can answer it. Right. Enzymes. Exactly. So enzymes, which serve as a catalyst, can lower the activation energy. Do you understand that, Ruby? So basically what an enzyme does is it basically decreases the activation energy. It takes it from up here to down here. So it makes the reaction move faster. Does that make sense? So that's what an enzyme does. Okay? All right, makes sense? Okay, now watch this next thing. Well, the next piece about this, which is pretty cool, is that we said this enzyme will lower the activation energy, right? Well, there's something called delta G. Has anybody ever heard of delta G? Okay. It stands for Gibbs free energy. Okay. So delta G stands for Gibbs free energy.